Very good morning to all participants. Today is the second day of our conference, the ICITDA conference, and indeed it is a pleasure to have you all in this beautiful morning. Hope everything is everyone is doing well today. And my name is Irving. I'll be guiding you all in this workshop session. We have here Dr. Hamwira Yacoob. Morning, Doctor.
Morning.
Okay. Dr. Hamwira will be our main and the only speaker for this workshop. And as a brief introduction, Dr. Hamwira is currently an assistant professor in Information and Communication Technology Department of International Islamic University, Malaysia. And Dr. Hamwira received his Ph.D. from there as well, if I'm mistaken.
Correct.
And his expertise is in the area of electroencephalography, or we call it EEG normally. Also in the area of machine learning, affective computing. And this morning, Dr. Hamwira will present his work on EEG data analysis. Yeah, we know that EEG data is from our brains merely sound, even though it looks like only like a signal, but it contains a lot of things that we can retrieve. Okay, Dr. Hamwira, you have like I think until 10 a.m. in Malaysia or 9 a.m. here in Indonesia. Okay, you have until 10 a.m. in Malaysia or 10 a.m. here. It's about 90 minutes or more or less before we start our Q&A session. And to all the participants, you can also type the question in the chat room or chat box. Okay, Doctor, you may start your session now.
Okay, thank you, Irving. I mean, it's a great pleasure to actually to be given a chance to share my experience in doing study in brain EEG study. So I have prepared a slide. Let me just let me know if you can see.
Wait, not yet. Okay.
Yeah. Alhamdulillah rabbil alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wasahbihi ajma'in. Rabbi shrah li sadri wa yassir li amri wa hlul 'uqdatam min lisani yafqahu qawli. Assalamualaikum. I hear voice.
Clear?
I hear some like some other voice. Some talking.
Yes, we share this room with other.
It's okay. So all right, let me just continue. So that's me. I am actually been working in this area. The topic that I have agreed to share is actually EEG data analysis. I've been working on this topic since 2011. It's not even 10 years yet. So it's fairly new to me. Probably the audience here know more than I do. What is EEG? EEG, as mentioned, is actually the electroencephalogram. Our brain it's capturing the electrical discharge that is produced by our brain. Brain, as we know, that it's actually the main organ of our body. Yeah, so that's the main organ of our body. So it's like a central processing unit. Okay, can you hear now? Okay.
Yes, we can hear you.
Okay. So so the brain is actually the central processing unit of human body. So everything is actually processed there. In theory, brain is actually communication is done when we sense when we are stimulated. So whatever we perceive is actually sent to the brain and is processed there. That is one way. That is called bottom up. Also, the brain is activated when we are actually thinking, when we are thinking about something and then we want to do an action. So that is a top down. So again, whatever it is, brain is actually the main processing unit. So brain contains a lot of neurons, and these neurons are actually from every part of our body. So the information is sent from every part of the body to the brain through neurotransmitters. Neurotransmitters are substances that are passed from one neuron to another neuron, and due to the passing, they also pass electrical signal. They also pass a change in hemoglobin, change in oxygen. So because of that, scientists in neuroscience, they have come up with different neuroimaging technique. So these neuroimaging techniques, these are techniques that are actually used or can be used to capture brain signal or brain activation. So EEG is one of that. If you look at the slide here, EEG is just it captures brain signal through electrical. So electrical discharge by brain is captured there. MEG is capturing the magnetic field that is discharged by the brain. And then we also have ECOG, we have ICNR, and we have fMRI. fMRI is more measuring the oxygen density in the brain, and also NIRs. So these are different techniques other than EEG that can be used to capture brain activation signals. Okay, of course, these neuroimaging techniques can be divided into either invasive or non-invasive. The invasive techniques are techniques that require operation, official procedure where we cut the scalp and then actually touch the brain. So that is invasive. So and then another one is we don't do the operation. We don't do surgery. We just do the you just capture from outside. So that is non-invasive. Among of these neuroimaging techniques, they are different, of course, in terms of cost, in terms of size and mobility. But of course, the main important thing, these different neuroimaging techniques, they are different in terms of the temporal and spatial. What is temporal? Temporal is actually the time resolution that a technique can capture. And also the spatial is the space, which is at what area can it capture or record. So in this case here, this graph or this plot, it just shows how the performance of different neuroimaging techniques in order to capture temporal and spatial information. The one in red here is actually invasive. If you see, for invasive neuroimaging techniques, they can capture up to the neuron level. It's very good at the neuron part. And also at a very good time recording at millisecond every second, because they can touch it. But again, it's invasive, where you have to cut and open the brain, and we don't want to do that. Other techniques nowadays, they have come up with different neuroimaging techniques that do not require an operation. So these, the one in the blue you see here, they are actually the one without doesn't require operation. So if you see EEG here, EEG falls under this part here. So it means that EEG can capture brain activation at millisecond, even more smaller than millisecond, but it cannot give a good information about where the location of the brain segment inside the brain. Because EEG is capturing the electrical discharge at the scalp, so it's not really at the source of the activation. Okay, so because of that, EEG has its own limitation. The limitation is actually the spatial or the space or the location, because it's only at the surface level, but it is very good at the temporal. So every time the brain changes, it can capture directly as compared to NIRF, NIRS, fMRIs, PET, PET and SPEC. This one here, it only captures the brain activation after a few seconds or after a few minutes. Okay, so EEG is not really a new study area. It has been studied since, I think, in 60s or even before that. And because of that, they have come up with different machine or different devices to capture EEG. Again, EEG is an electrical discharge that is captured due to the brain activation. Okay, so there are different models of brain activation here. Okay, so at our lab here, what we have, I've been working on this subject since 2011. I've been experiencing different types of devices. Okay, let me see. We are going to see one of these devices later. Okay, as I mentioned, EEG is good in terms of capturing the temporal information, but it has limitation in capturing the spatial information. So because of that, there are different ways people study emotion. I mean EEG. So I'm just capturing some ways of studying EEG. EEG can be studied using the assisted software tools. In other words, nowadays there are already many software tools that can be used to capture or to visualize EEG. So these software tools, for example, Accelerator, BESA, EEG Lab, and these software tools that are actually being used by neuroscience, more on neuroscience, because they really want to understand the locality of the brain activation. Again, that is very challenging because we know EEG have very poor spatial resolution. Okay, so because of that, there are also studies on EEG to try to predict the source of brain activation from whatever captured at the scalp. Try to understand the source where it is actually occurring. So that area is known as source localization. Another area is event-related potential. I'm going to go talk about these, some of these again later, and then also profiling, and then finally the more interesting is brain-computer interface. Brain-computer interface is when we make use of the brain signal and try to decode it and try to perform something through computers. Okay, any questions so far? It's like giving a lecture.
No, Doctor, you can carry on.
Yeah. Because it's as we mentioned, as I mentioned earlier, EEG is captured at the scalp level only, on the surface only. Therefore, it's very bad in capturing the spatial, the locality where it occurs. So therefore, there are studies looking at how, which part of the brain, is activated. Why they want to do that? Because it is very important. I mean, when they want to perform surgery, especially doctors, if they want to perform surgeries, they don't want just to open the brain and try to pinpoint, try and error to find the organ, because brain is very sensitive organ, and it's actually encapsulated in a skull. So, you know, it's not easy to get into the brain. You have to drill. So, so if we get prior information on where to go, go when we do the surgery, it will be better. So therefore, they do study for source localization. What is source localization? I mentioned it earlier. So if a brain is actually captured at a scalp, they want to know where exactly in the brain that activation occurs. It is not that easy, because at one point or at one source, we can have many answers. Okay, we can have many solutions. So the main question is where exactly is the one. So that's one of the area of the study that they are doing now. Okay, another area is the brain-computer interface. Okay, where is my, okay, the brain-computer interface, as I mentioned earlier, brain-computer interface is fairly new. It's basically take care of the, a system that reads brain signal and then process it in real time and give a prompt response. This is now possible because now the EEG recording is now, we have more mobile or more, it's smaller and easy to carry. Okay, so one of my final year project is actually working on it. Okay, another way of studying EEG is through event-related potential. What is event-related potential? Is actually looking at understanding the brain pattern. Okay, brain pattern is actually captured and visualized in terms of wave or signals. So it is captured from in terms of time. So through ERP, what it tried to do is to find a general pattern through averaging. So for example, in this case here, there are two tasks that are performed and the EEG is recorded during that task. The tasks are X and O. I don't remember what are X and O. There are different tasks. X and O, maybe one is eating, another one is watching TV from the same person. So they really want to study what happened when this person is, how the brain looks like, how the pattern looks like when they are doing these different tasks. The challenge is the brain signal is not, we cannot see it in that way. It's very subtle. We cannot really find the way as it is. So therefore, what they do, they apply the event-related potential, try to average, try to somehow translate each parts into a more generalized parts. And from there, they can perform classification. Okay, what's next? That's how people have been studying EEG. In my experience, 11 years, it's 9 years of studying in this area, we are in our research group are proposing a technique where we use machine learning or computational model to analyze brain signal, and then we call that technique as the Neuro-Affective Profiling. What is that? Neuro is brain, affective is affection or emotion. So we make use of the emotion to profile or to understand the brain activation. And we apply machine learning technique as usual. When we are talking about machine learning technique, it consists of several steps. The standard steps are data acquisition, feature extraction, training, and classification. So those are the techniques. So how does the model works is that we use emotional EEG or EEG that is recorded during emotional stimulation. We use that EEG data and train it to become a machine learning model. So that machine learning model, the objective of that machine learning is to classify what is the state of emotion at that time, whether it's happy, whether it's sad, or it's positive or negative. So now, once we already have a emotion model, we use EEG recording on different tasks, non-emotional tasks, driving, studying, sleeping. We try to understand, we run these tasks on the emotional model. We use the emotion as the reference. So in other words, we want to understand how this non-emotional brain activation behave when the person is using this task, doing this task. Okay, so we have been doing many areas in that. Through our technique, we can actually see the dynamic of emotion, the dynamic of emotional states, while a person is doing a dynamic task. Normally, when we are talking about the existing emotion recognition technique, they are actually just summarizing an emotion at a certain time. So, for example, it's not instantaneous. It after a few minutes or after a few period. But through this technique, we are aiming to capture the emotional changes or dynamic at very instance. Okay, at very instant. So this is the technique that we use. We are going to talk about this again. So what I'm trying to show here is that we can capture the brain changes when a person is driving at that particular moment or at that particular instance. And then we also use this technique to understand, to perform the ADHD profiling. This one here, when we talk about EEG, normally they will go to ADHD. They will go to the learning disability kind of study. So of course, there are different areas. They looked at the behavior. They looked at the activation through the visualization. But here we are proposing a technique that actually we use machine learning to understand, to perform ADHD profiling through emotion stimulation. So we use emotion stimulation. We try to understand the ADHD subject through their emotion. So we get their emotion stimulated, and then we ask them to perform a standard test that is used to profile ADHD. That is to perform motor imitation. So person with ADHD, it will be difficult for them to actually to interact, to follow our order. They don't follow order. So that's why this task is actually invented. So ask them to do that. Then we study the brain pattern, or rather the emotional dynamic when they perform that task. So we see the results down here. There are two results here. The left one here, it shows a normal subject, I mean non-ADHD subject. In other words, when we try to communicate with them, when we try to ask them to follow whatever is shown in the video, they actually doing it. The brain is actually working. While on the other hand, a group of ADHD subjects, there's no activity or no changes in the emotion when they actually doing or performing the task. Okay, so that is one. Another one is to do dyslexic profiling. So through dyslexic profiling, there is a certain task to do it. Dyslexic is actually syndrome or disorder where it's a learning disorder where normally it occurs in adults and kids, but normally a dyslexic patient, they cannot read properly. I mean, they cannot see words. I mean, not words, characters. For example, E, they see it they see it in upside down, different patterns. So it's very crucial to really, if we can capture this at the early age, because because this kind of disorder can be rectified, can be intervened, in other words, can be corrected. We've studied in our research group, we studied how using the neuro-affective profiling, we try to understand the behavior of or the emotional dynamic of the subject, dyslexic subject, when they close their eyes in the resting state. We can see they actually can be distinguished. Okay. And then we also have mood profiling, it's the same thing. In this case, we are looking at mood. And also this technique can be also, it's really applicable or practical when we want to study the driving behavior. In this case here, we had studied with Academy Laut Malaysia, is ALAM. We tried to, ALAM, they actually designing route for sheep. So they need to sell their product, but in order to sell the product, they want to put a value added. So they asked us to come into the picture. We try to capture dia punya captain stress level when they are maneuvering the ship. Okay, this is just another example. More examples. Okay, so I'm just going to go straight to the neuro-affective profiling, or in other words, the EEG data analysis that I've been experiencing. So first thing is the data acquisition. Data acquisition is, of course, not new to all of us. It's actually, okay, I need to set up. It's the part where we get the data. And then after that, we have feature extraction, where we try to extract or select features for training and classification. These are basic steps in machine learning classification. So in data collection, there are several components or elements we want to look at. So what you see on the screen now is actually a setup, a data collection setup that we normally do, where we have a stimulation screen. So the main thing is the stimulation. What we want to stimulate the emotion, we want to stimulate the brain. So what we do, we show some stimuli that it has been studied then to stimulate the brain. Okay, that's the first thing. Another part is the EEG recording part. So the EEG recording part involve the electrodes and also the amplifier, the EEG machine. So that's another part. I'm going to go through with you each of these steps later. And then most importantly is the protocol or paradigm. Okay. Or paradigm. Okay, I'm going to talk about the paradigm first. What is protocol and paradigm? So normally, when we do data collection on EEG, what we do, first what we need to do before recording, we need to talk to the subject. We need to brief the subject that what we are doing. We are going to take the recording, and at this time also, we need to get their consent, their approval on what we are about to do on them. At this time also, we get the demographic information such as gender, age, whatever, and so on and so forth. And next is during recording. So during recording, this is the steps, or these are the procedures or protocol, or in medical domain, they call this as the paradigm. It is a paradigm. It is the activities that we do when we do the recording. So normally we record the resting states. Normally that's the first part. Eyes closed and eyes open, and then we perform emotion stimulation, and then we perform non-emotional task. Let me just set up my machine here. It was okay just now. Okay, it's there. All right. Okay, data stimulation. How brain is stimulated is well, our brain is stimulated through through seeing. We see, or we listen, we smell, we feel and think. I mean, all the senses that we have. That's how brain is actually stimulated. Of course, thing occurs at the brain. We think about it and then it occurs. So if you see, you remember that the first thing we do is to stimulate the emotion. Why we want to stimulate emotion? Because based on our model, we use emotion as the reference. So how do we stimulate emotion? Emotion can also be stimulated through these 5 techniques. Okay, there are a number of data set or stimuli set that are available already. For example, in the image, in the Neuro-Affective Picture Database, is a database that consists of non-facial images that have been validated or verified to have to induce a certain kind of emotion. So there are 730 stimuli. So these are pictures. I'm just going to go through it very quick. So these are just pictures and non-facial pictures that have been studied, that have been validated to have some emotional impact to the viewers. When someone look at it, they have emotional impact. They report an emotional impact. So that is a non-facial stimuli. They also facial images. There are many facial images, and then we also have audio. When we listen to music, sometimes we get emotional. So they also study that. So for example, the first row here, there are 795 pieces of music, emotional music that have been validated. Then video. Okay, so these are different types of stimuli set that can be used to invoke emotion. Okay, in our research group, I mean, I have the chance to work with Dr. Dini. She presented yesterday. I think she also has some papers also today. She also developed stimuli set in terms of video clips. So what happened is that we gathered video clips from videos, of course, from YouTube. So what we do, we get a number of subjects to evaluate the videos that we selected. So using the self-assessment mannequin. So this is how emotion is being tagged or emotion is being quantified. So for each video, we have hundreds of evaluators. So based on the evaluation by these 100 evaluators, we know what kind of video it is. We get the normative summary of that. So that is the stimulation. So okay, next is actually the data recording or EEG recording. I am going, as I mentioned, there are several ways of capturing or recording EEG data. These are some of the tools that we have here. So I'm going to share with you my, I'm going to stop sharing, but rather I am going to give you a view on my, Okay, so there are different machines that we already have. For example, this one here, this is emotive. This emotive here is actually a wireless neuro headset that we can put on the brain and put on the scalp, and we'll be able to see it, to see the brain pattern. So again, you have different channels, and then we have different caps, okay, different caps to actually that can be put on your knee. I don't know if I can show both. I'm not sure, but what I want to show you now, there is one machine here I have here. This is called a brain marker machine. It has been connected to my other computer. So what you have here, this is holes for electrodes. So the main thing for data collection is the electrodes. So this is an example of electrodes. So we have electrodes here. So I have a lot of electrodes, many electrodes. So this part here is the part where we paste it on our scalp. Okay, we paste it on our scalp and based on the location in the scalp. So if you see this diagram here, they are different levels. We have FP1, FP2, F7, F3, F7, FZ, F4, and F8. So these basically are the location of electrodes on the scalp. Okay, so for example, if I want to record my FP1 or FP2, I'm going to put it here. Okay, so what I need to do now, I'm going to switch to my camera, to the front camera. Bear with me. I will need conductive solution and put it on the corresponding location. And the location is actually based on a standard. It's called 1020 standard. So it is actually a standard. It's been accepted worldwide on how to place EEG electrodes. Now I'm going to share with you my Google Meet. Okay, let me. It's very interesting, yeah, when we do this kind of virtual workshop, when we want to show the devices. Bear with me here. I need to. The point is, I have my software in different machine. Okay, I have Q. Okay. Okay, I hope you can see my my screen now, and also my yeah. So what I'm going to do now, I am actually going to put the electrode on my forehead. Okay, that is at the location of FP2. Can you see that? I hope you can see. But anyway. Okay, let me try that. Okay, I hope you can see my both of my the software that I'm using and also my screen, because now I'm actually putting the electrode on my scalp, okay, at a certain location, and over here I'm going to do this. I'm going to do the recording. So this is a software that comes with the device. Yeah. So what I want to do, I want to do the recording. So I perform the recording. I add a new patient. Let's just say the name of the patient is me. Okay. And then I can fill up the particulars and then I save it. So me is there. So next, what I want to do, I want to select the patient or the me. So what I want to do, I want to perform the recording. Okay, I want to perform recording on EEG. So on here, I select the all EEG, all signals. Okay, and I want to select the location that I want to record. I'm talking about the FP2. FP2, and for fun, I'm just selecting any point, let's say 0, 2. If you notice, oh, you cannot see that. Okay, anyway, there is it does not really appear, but of course, actually I can select. So I select my name, and then I get it connected. Select again, FP2 and O2. And I want to play. If you see, now some signals are coming out. That is at the location of FP2 and 02. FP2 and 02. Of course, these signals are noisy. We are not really, doing it properly. Just doing it just for the sake of demo. You see, the 02 is the part where I didn't put electrode, so nothing is occurring there. Where FP2 is the one that I put electrode, and there something is going on there. So then what I do next is actually I need to, that is just to play. So what we can do, we can play and record. So when I record, I can just give any name there. Okay, I just give any name. Me EEG. So we can use timers, so how long we want the recording to be done, and so on and so forth. So again, this one here is to do recording. Okay, so that is how EEG is being recorded. When it is recorded, we will get the data in terms of, so if we go back, stop. I don't remember what's the name of that. So let's just stop. We're done. We stopped already. We go back to our knee. We go to the patient data. It's me. So that I go to the file manager. So under me, what was the name of us? Under me, there is a me EEG there. So this data, then what we do, we take it and then copy it into our machine, and we then use that data as the the source or the training data for our machine learning. So I'm going to stop that one here. I think that's it. But that one is just data. What is data?
Collection.
Thank you. Okay. 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 There is one question already.
Yes, there's one question, but training data.
Training data. We have not gone through that yet. Okay, I'm going to continue before I answer that question. Okay. Okay. Okay, I'm going to share my slide again. My slide.
I think that's a problem with Dr. Hamwira, so we need to wait a bit for him to rejoin the workshop. Sorry, everyone. Okay, while we are waiting for Dr. Hamwira to rejoin the workshop, you can also okay, you can start to think certain question, and then you may ask, you may type your question to the chat room, or probably those participants from Indonesia, you can also type your question in Bahasa. I will let Dr. Hamwira know about it. Don't worry.
Hello. Hello.
Yes, Doctor. Yes, Dr. Dini.
Here, yes. Okay, so maybe I will give some explanation. Dr. Hamwira maybe have some technical problem at the moment. So maybe just now he demonstrate on how to collect the EEG data. Then from that phase, we will continue to do the feature extraction and also continue to do the classification for the machine learning training. So the question is about, the first question I think is about the filtering. So the filtering process is under the pre-processing part. So when you collect the EEG data, you will get the raw signal, and sometimes it still have the noise and artifact. We have to do some pre-processing technique to clean up the data. So some filtering technique you can apply for the pre-processing phase. For example, you can use the Butterwood filter, or maybe if you're familiar with others filtering technique, you also can apply it there. Then after the filtering process, meaning your data is ready to use. Then after the filtering, you can go to the feature extraction, where you can extract the features from your signal. So in the feature extraction technique, you can use time domain analysis or frequency domain. So it's depend from which particular technique you want to get the information from your EEG raw data. Even if you want to combine time domain and frequency domain, also possible. Okay, so what else? Yeah, maybe I try.
It's okay. For your information, this is Dr. Dini. Dr. Dini is a research partner of Dr. Hamwira in neurocomputing. So she just explained about noise filtering, right, Doctor? To answer the
Yes,
Mr.
correct.
Haki.
Okay,
One
so
of the
maybe
question.
another question from Pak Hendra Bunyamin. Why
Yes,
you did not include part of non-emotion EEG in the train set so that the model can also learn the non-emotion part? So it's also possible to collect the non-emotion data, but here we only want to give the sample. And also for the protocol, I think Dr. Hamwira also showing it's not only collect the emotion data, we also collect others data, for example, the resting state and so on. Because why we choose the emotion, we also have the interest on the affective computing. That's why we also what we call it the highlight on the emotion. Because from emotion, we can analyze not only emotional state, we can also analyze mood, we can also analyze personality. So we can get more if we collect emotion data, something like that. So in our research group, we also analyze non-emotion data. For example, we have the research on how to identify kids with autism, kids with dyslexic, and also kids with ADHD. Okay, so why we concentrate on kids? Because kids still have what you call it, the brain development process. So they are still in the brain development process. So once we identify something not correct with the brain development, we still have some time to do some treatment, for example, to help kids with the kind of problem.
Okay, Dr. Hamwira is back.
All right.
Sorry about that.
Thank you, Dr. Dini.
Dr. Dini is, I mean, he also has a lot of, we had experience together learning this journey. So I'm just going to continue from my slide. I forgot to actually put the name. I'm going to share the, thank you, Dr. Dini. Let me just share the slide. So when we do the recording, we get this kind of data. So the device that I used just now is actually is a machine that consists of 19 channels. So the data is recorded and it's normally in this form here, where the columns represent the channels and also the rows represent the samples or digital or time sampling. Yeah. So what we do now it's easy to see to actually manipulate it. So what happened next is again, this one is just a raw data. What we want to do is to do the feature extraction. Feature extraction, we want to get the features out of it. So common features that we normally do, we do signal pre-processing. Of course, in pre-processing, what we do, we select, we clean up the data. If it's in machine learning, signal pre-processing is performed to get rid of the missing data. Okay. And then we have feature extraction and also labeling, because now when we have the data, we don't know which one is what emotion. So then we have to label, because the data that we have is mainly EEG. It's only microvolts. Okay. So a signal, I mean, I don't want to talk about this because I'm sure most of you already here know what signal is. I'm very expert in signal processing. A signal just like EEG signal, is actually composed of several other signals. It's an addition of other signals. Okay, so for EEG, it composed of signals between 0 to 55 hertz, or rather 60 hertz, I'm mistaken. It's 40 hertz, okay? 0 to 40 hertz. So when we record it, normally we also record the power, so the surrounding noise. So that's what we want to do during pre-processing. We want to get rid of that. So we want to select the bands that we want to study. It's either delta, theta, alpha, beta, and gamma. So that's what we do first in pre-processing. As I mentioned, when we looking at the signal, we can look at a signal in terms of time domain or in the frequency domain. For EEG, we know we want to only select a frequency between 0 to 40. It depends on our study. For our study, for this study, normally for emotion, we look at theta and alpha. Why theta and alpha? Delta is a wave produced when we are sleeping, when we are relaxed. Theta, when we are awake, we are calm. Alpha is somehow our brain is working. So emotion, in other studies, emotion occurs between theta and alpha. Therefore, we select in pre-processing, we select the EEG signals within that frequency range. Okay, so so here on the left is actually the EEG signal in terms of time. So you have time and also voltage. So as from the previous slide, in time we can actually the signal is composed of different frequencies. So if you look at in a 3D, like this one, we look at from the top. These are things that we can see. This is the time. This is the frequency. Okay, so we can see how this actually and then the color represent the voltage. So it's three-dimensional. So so we want to make use of that. We see this is in a spectral or spectrogram, spectral domain. We see there are frequency that we want to get rid. For example, and this one here is we want to only capture. We are considering frequency between 0 to theta. Theta was about, how much was that? 13, alpha, theta and alpha. So it's 13. So this range here. So this is the frequency. It's a normalized frequency, although it's talking about 0 to 55, but it has been normalized. So it's a rescale. And this is the time. Okay, the time is actually the samples that we had before. So looking at one electrode, one channel, we can now, from the spectrogram, we can calculate the power spectral density. So we get the average of each time across this. That becomes the power spectral density. So this power spectral density will become our features, the values of features for the corresponding channel or the corresponding electrodes. So for this case here, it's for C3. C3 is a channel or a position on the scalp. So we can do that for all the channels. In this example, I'm looking at 8 channels. Okay, so that's the channels, and we can rearrange. That's the sample. These are the power spectral density. It's from the time domain. We translate into frequency domain. We calculate the power spectral density. So that becomes the input. So the first row is the first time instance. The first row is the first sample. So this sample consists of 8 features. Second row, 8 features. So they are all time instances. So that becomes the feature set for our machine learning training. But again, the question is, when we talk about machine learning, when we talk about classification, what we want to know is the class or the label that we want to train. Okay, so in this case here, we need to perform the labeling. How do we perform the labeling? The labeling is done based on the emotion theory. So in emotion study, there are different ways how people, how scientists or psychologists quantify or measure emotion. These are many techniques, three-dimensional and so on and so forth. But fundamentally, it based on a two-dimensional circumplex model of affect, which is emotion can be quantified through valence and arousal, through positive or negative, and the intensity, aroused or sleepy. So that's how emotion is being quantified. But for this purpose of our study, we normally generalize it. Whatever emotion under this quadrant is considered as positive emotion. This quadrant is negative emotion. The one above here is aroused, and this one here is sleepy or boring. Okay, so that's what we do. So that based on this model, we can now actually label our samples or time samples. So in this demo, I'm just looking at positive and negative emotion. Okay. So I can label. So at the last column, what I do, I just label it based on the training sample. So of course, how do I know? Because I know based on the duration when I record the emotional stimulation, I know the duration. I just divide it by 2 or by 4, and we kind of like can estimate which part is actually for emotion 1, which part is for negative 1 emotion, or negative or positive emotion. So that is the labeling or sampling. So next, what we want to do, this one I think is straightforward. What you want to do, you want to do the training, and when you get the training, you will do the same thing for non-emotional. Then from there, we know what kind of output we should get. Any question? If you have question, can answer.
So far, no, but wait, is there any, doctor, if we put the electrode here, let's say, okay, in my, okay, on my head, it will, is there any similar pattern if we put in others for
I know what I mean. So no, because they are different. I mean, if you put in your hand, for example, right? So it's different. EEG falls between 0 to 55. So of course, if you just put it anywhere on your body, you can still capture that, but it does not. It can still capture that frequency, but it does not. It's not from your brain because it might not be even there because you have to filter, because it's only between 0 to 55. If you put somewhere else, maybe you can see the signal, the raw signal is there. It might not even EEG there.
Okay.
When we record, yeah, you can see, but you know, you need to do the filtering.
Okay. It's okay. This that's another question actually from Mr. Bayhaki about positive emotion related to delta and negative related to alpha.
Okay. Okay, I cannot see
okay. He's not that clear about the positive emotion related to delta and negative related to alpha. He wants to know.
Okay. Is positive? Is positive emotion is related to delta and negative
to alpha.
Okay. Of course, there are many studies on this. But for delta is normally it's when we are sleepy, when we are sleeping. It's possibly when negative emotion, when we are so down, it's possibly the data is also there. So again, through this technique, it's really up to us to identify which bands we want to study. But again, in other research, delta is mainly when we are sleeping. So unlikely we can see a brain some kind of pattern there when we have some emotion. The argument is probably true when we're talking about positive emotion related to delta is when we are calm. When we are calm, we are not doing, our brain is not exhaustive. It's not exhausted. We calm, we like sleeping, we are no emotion. So that's why delta is there. But well, when you're negative, somehow you are intense. So normally theta alpha is when we are working, our brain is really like mungkin runsing lah masa tu.
Okay. So it will be automatically appear the signal, right?
That is when we are looking at the signal. Yeah.
Okay, I think you may continue. Okay, Mr. Bayhaqi, so it is depend on what we define or not?
Yeah, looking at different, we are looking at different study area. We will agree that emotion, positive emotion might be related to alpha because probably argument is that because you are calm, you are not doing any, your brain is not runsing, it's not, but when negative, your brain is really thinking about something, so alpha is there. So in this study here, we can actually pick, because in this study, what we want to do, we are using the emotion as the reference. So it's really, yes, depends on us to pick what kind of input as the features. So we can say that we want to just pick the delta because we want to see the task, the non-emotional task is positive or negative emotion. I hope
I think that is clear. Okay, Dr. You can continue to your on your presentation.
Okay, I actually have okay, let me. No, I am actually I have shared in the I've shared some sample codes that you can use when you want to perform this kind of technique. But I need to open my Python. So so this is done using Python. I mean, of course, we had experiences in MATLAB. So it's any languages that you prefer to use, but the concept should be the same. Okay. It may a little bit time to run. Yeah. Okay. Still running. Okay. Probably I can get any question, if any. I run my Python just now, but when the computer is down, it's automatically off as well. So I need to restart my Python.
Okay.
So yeah. So any question? If you don't have that, probably to know more about this, actually, my students are actually presenting this afternoon. So you can see the demo that I have is actually a very fundamental one. Is actually is done in a code basis. There is no interface. So one of my paper produced by my student Muhammad Farhad, he's here, that he's presenting a toolkit, or rather a software that capture all these tasks, the pre-processing, the training, and also the classification all in one. So that's what one. And if you want to know more, you can go to that. And also have another study that actually looking at the emotional behavior when a person is playing game. So want to understand how the game design affect the emotion. Okay, and also have a paper with Dr. Dini here. This one is more technical. Now we're looking at different filtering techniques when we want to perform EEG signal analysis.
Doctor, how about infant, doctor? Is you have any experience on analyzing EEG from infants?
No, actually we don't. We started with preschoolers because
is there any difficulties performing EEG on infants?
I think it will be easier than the preschoolers because they are just sleep. They are just don't move. The subjects that we have been dealing with, they have problem in ADHD particularly. They don't follow instruction. So sometimes we cannot touch their head and they will run away. So that's difficult. But for infants, I believe it will be smoother in terms of data collection. Is easier than the children. Because infant, they are just laying down there. The worst they will do just to cry. But no, but we don't have experience.
Okay, I thought collecting EEG from infants will be more difficult. I mean, in my opinion. But if you say no, then okay then.
Yeah, but there are studies actually doing that, doing the for infants.
Okay.
Okay. Any other question? I mean,
yeah, I think.
I'm not sure if I want to. Can you see what I'm sharing? What the code?
Not yet. You just shared the paper.
Okay, Agam, perhaps there's gonna be issue of ethics for collecting data for info. Okay. Yeah, I mean, issues for the ethics is for everybody actually. When we want to do the data collection, that is also the challenge where we need to get the ethical approval. Is the same thing. The ethical approval, because that's why we need to get their consent or their agreement.
I think the consent for infants can be from their parents.
even the kids that we are having also from
parents. I see. I see.
Unless it's adults. Anyway, so I think I only have few minutes. I'm not sure whether
you still have a lot of time. Don't worry, because we mix also with the Q&A session now. It's okay. You may carry on with your presentation until the testing stage.
So I don't really have much to show. In the folder that I shared, I'm not sure whether you get it, but I'm just sharing you a very simple code where this process can actually be implemented using using Python. And in the code here, what I show, I'm just showing how we can do the process using one channel, and of course the result is not accurate as I mean as we have more channels. So if you go to this this here, this code here, I'm just going to go through with you. I define the EEG code.csv. So that is the file that we actually get when we save through the system. But this normally, different machine or different software, they will have different types of data. So the challenge here is actually to find the converter from that format to CSV or text. Why? Because we need a raw data. So normally these providers, the EEG solution, they have their own format because they don't want us to hijack, I think. So anyway, so once we have that data, the data is in terms of columns and rows. The columns are the channels, and the rows are the time samples. So what I put here, I put post and neg here is actually the label, the labeling for the emotion labeling. So what I'm doing here, this code here, training-1.py is a code that actually used to train the model. So I have here some parameters. Fs is the sampling frequency, and then the lower cut, I'm talking about theta, from theta, and then the high cut for filtering, I'm talking about alpha. So I want to, from the original signal, I want to capture, or I want to capture from 4 to 13 bands only. That will be my output or the analysis. So of course I just use any band pass filter here. I mean, there are many techniques or many ways of performing band pass filter or filtering. You know, and this is just one way of it. So what I do here, first I read the file, the original file in column and rows, and then I would calculate the total samples. Okay, because the total samples, when we perform the recording, we might have more than what we want, because normally when we start the recording, we start earlier and then finish it later, a few seconds later. So what we want to do now, we want to have a very consistent number of samples. So for in this case, I just want to have about 60 samples. So then for each of that, okay, because the way the emotional data is being recorded, or emotional EEG recorded, it is in sequence. That is from happy, and then from happy to, I think, 1 minute happy, 1 minute sad, and 1 minute calm, and 1 minute fear. So they are in one file. Okay, so here is just trimming just to have the same consistent number of samples for different emotion. And then after that, after we do that, we can now do the filtering. Filtering here, I'm not going to go through this because this one here is really signal processing. Different techniques. Here we use the butterfly, the bandpass processing. So we specify the lower band and the high band. I mean, from 3, what did I say just now? From 3 to, from 4 to 13, yeah, that is from theta to alpha only. So I do that. This part here, I do for all of the data sets I have, emotion, happy, happy, sad, fear, sad, and also calm. And then I combine them. And becomes the whole table, and also label them. So for happy, I label it as 1, and fear, if you refer to the quadrant I showed earlier, happy should be positive, fear should be negative, sad also negative quadrant, and then positive quadrant. So I split these two, not split, I label them as negative or positive 1. And then here is just to combine all the data, so it becomes a complete data set. So that is called affective data set. So that is my affective data set. So then what I do, I'm done with the processing, I do the training. So the training in this case here, my affective data sets consist of only 2 columns, which is 1 channel and the class or the label. Okay, so in more complicated, we can take 19 channels. So that means this part here, we have longer code because we will have to do it for each channel. But for my student, he actually compiled it and has made a function for that. So that means, you might want to use his solution. So anyway, so I'm just showing this to show how it works. So we have X. X is the affective, is the features, the input. In this case, only have 1 input and then 1 output. And then in this case here, I use MLP. MLP is a machine learning algorithm that is used for classification. In this case here, I use regressor. Why I use regressor? Because I want the output to be in continuous number. In Python, if we use MLP classifier, it will give discrete values. It's either 0 or -1. But in this study, I want to have the output to be continuous numbers so that when I plot, I can see the changes, not only 0 and 1. So that is when I use the MLP. And then, so then what we do the training. So that's the training. We feed the data into the model. The model is called EMO model. And you should get the model. So then what I do, I save the model in our desktop, and the model is saved as emo_model.sav. So if I run this, okay, so it's trained. So if I go to my folder, I should be getting this file saved. So that is actually my model. Okay, so inside the folder that I shared, I also shared the classify -1. So that is actually the second part where I actually put some classify 1. Put some errors, not errors lah. I put something here. There are errors where I don't, for here in this case, EEG file, I don't put it there, mode file, just for you to try out. And then also low cut, what you want to do. So in this case here, and then how you want to do the pre-processing, also classification. So in this case here, our EEG file, if I can show you, let me just show you through here in the folder that I shared with you. EEG. In the folder, there are 4 files that I shared. The first one is the training-1, that is for training. Then the data for training is FO1_emo EEG. This is the EEG for emotional data. And then for testing or classification, I have FO1_EC EEG. That's for eyes closed. Then I share with you the classify. That classify is actually this file that does not have, have some missing parts. So, so if you will be able to complete it, so basically what you want to do is you want to specify the EEG file now. It's the EC or eyes closed, not the emotion. And then the model file is the model that we saved earlier. And we use the same frequency, because why we use the same frequency? Because we train using the same frequency. And then this one here are the same, it's just filtering. And then later on what we do the same thing, like the same thing like the previous one, the emotion. We do the filtering, pre-processing, and then finally what we do, we perform the predict, or we perform the classification. So so if I run this, I should be getting values. These values are values that I obtain from the eyes closed. Okay, so from here, we get several values. So of course, this one is here is still not, it's still raw and not so good, because we are only depending only one feature, and it's just not really reflecting, it's not really performing classification. In order to do classification, we need to put some threshold value. In other words, if it's negative, we put it as a negative. If it's positive, we put it as negative, positive. The reason I put it in this continuous number, so that we can see the dynamic or the changes of the signal.
So how about the accuracy, doctor? I mean, in your, let's say, your full work, your full research about this categorization, you propose 4 categorization, right, for the effective, what is it, set and so on. How about the accuracy based on your research?
Okay, the accuracy, yeah, because of course the accuracy is actually what is, we cannot find the accuracy of the non-emotional data.
How about the emission?
We are looking at the emotion. So of course, before we use that, before we use that model, before we decide to use the model, we want to calculate the accuracy first.
Okay, so you get any
So the accuracy, what I mean by accuracy is that we are training and testing the model using the same data.
Okay, so did you get any percentage for the current one?
Okay, so normally what we want to do before we proceed, before we save the emotional reference, the emotional model, for the non-emotional, we need to make sure it is with a high accuracy. So normally we want to have 90% accuracy.
Okay.
Only then we say that, oh, this is a good classifier. Only then we apply it on the non-emotional data.
Oh, okay.
So so in other words, it's kind of like a transfer learning. We are training it using different data, but we run it on different data. We train it using emotion, but we run it
Is that okay?
It's a transfer learning. I think.
Is it okay?
It is yeah, it's okay because it's based on the emotion. It's the same. It's the same data.
Okay.
The way it's the same. This time it's still EEG. It still have the same features, but different scenario.
Okay. Someone is asking, Mr. Bayhaki is asking about the code and the data set. Will you share to
Okay,
us?
sure. I can share with you, but again, but that one is very simple. It's only one channel. You will not get a good result. You need more channels. You can go to my student's presentation. He has come up with the. I will share the code. It's already in the link. Do you have the link?
Link in where? In.
Okay, let me just get the link and then share in the chat room.
Okay. Okay. Another question, doctor. Okay.
Yeah.
Another question is from Mr. Ahmad. Previously mentioned that the sample data were obtained from children. Can we use a sample data from adults, and what are the possible challenges that we will experience when using this data?
Okay, can we use technically? Yes.
Yes.
Because as I said,
Of course, yes.
It's the same type of data, but we always refer. So when we study this, we don't do it blindly. We always refer to the neuroscience. What are their findings? So, for example, even in terms of feature the band selection, also we don't just put any bands we want, because based on their studies, they say that emotion only from this to this. So we filter in that sense. So when they say that that the thinking is occurs at that point, you know, that again, I have not mentioned this. When the brain is actually has different parts, the frontal parts, occipital part, temporal part, and parietal parts. So the locality as well. So we based on the other research as well, which part is significant. So to answer that question, it's really interesting to see what is the outcome. We haven't tried it yet.
Okay. Okay. So another question is, what classifiers that you use for the classification problem?
I use normally for this one I use MLP, multi-layer perceptron.
Perceptron. Yes.
MLP, ANN, artificial neural network.
Yes.
But of course, that's not the only classifier you can use. We have tried other classifiers. I have tried SVMs, a support vector machine, but support vector machine, it's 0 or 1, it's discrete, I mean, of course, it can also cater for multi-classes, but normally it's good to distinguish between two, I mean, to perform classification, not regression. In this case here, because we want to see the dynamic, we want to get the output to be continuous number.
Okay. So you will share the link for the code.
Yes, I am.
The set.
I'm getting it now.
So about the pattern, doctor. You mentioned your pattern, the 4 pattern that you have is based on the type of signal, right? Alpha, alpha and so on, right? Yeah, the pattern that you mentioned in your work. Is there any other common pattern of our brain signal instead of pattern based on the type of signal? So let's say for this kind of signal, then we can say, oh, this person is angry or something like that.
Yes, I mean they do that study. That's how they actually come when they say alpha and theta and alpha is actually for emotion. Yes, there are also studies that are actually looking at certain bands for certain emotion.
Okay.
That's the previous question. They said that delta is positive, alpha is negative. There are also other studies that are actually going towards that direction, where actually try to correlate alpha, I mean, certain bands or a combination of certain bands to a certain emotion. But again, it goes back to how you define emotion, how you want to quantify emotion. In this case here, we are just quantifying emotion based on positive or negative, arousal and boring or not aroused. Again, it really depends on which model you use when you want to define emotion. Some studies, they are looking at 6 states of emotion. So if you remember, there are different schemes that psychologists have come up to understand emotion.
Is there, this is just my curiosity, is there anything to do between EEG signal and what we have in mind? For example, what we want to say, is there anything to do with EEG?
Why you scared? Maybe we can try. Well, it's really it's really a lot of opportunities to explore the EEG signals, because when you say that, it really depends of what kind of classifier or what kind of model that we want to use. I know there are studies that are actually using the brain signal to spell words. So of course, to spell words. So of course, we need a certain, we need a trainer with classifier to perform a specific task. I mean, of course, probably that speller cannot be used to capture the emotion. We need different classifier for that. So what kind, when we're talking about what you have in your brain, what we need to know what kind of classification of the thing that you're thinking on the brain.
To some extent, it is possible probably in the future that we can read someone's mind using EEG. Right? It's like in X-Men, something like that.
Yeah, I mean, I would agree. But again, it's based on what kind of features that we're looking at and what kind of classifiers we use. But very interesting, that question. I remember this question was really asked to me before I joined IIUM back then in 2004. I started studying EEG is 2011, 2004. At that time, during the interview, they asked about something, but I remember I read somewhere that they were actually a husband and wife. They were actually doing study on this brain, but they implant a chip in their head somehow to communicate. But again, that one is really, you know, like very depth in the brain.
Okay.
I'm sure there are studies towards that as well.
Oh, nice. It will be very interesting if we can read someone's mind.
You are accurate.
Okay. I think I will also open the question to others participant. Please, participant, you may also raise your hand if you want to ask other questions. Please. I still have a lot of questions actually, but I will.
You can. Dr. Dini is here probably. But Dr. Dini is here. Probably she also can give some feedback or discussion. Dr. Dini is here, right?
Yeah, she was here, but
Okay.
I'm not really sure.
Okay. Sorry, Pak Haki, I was copying the link. So
Yes.
can you get the link? Can you read the link? I mean, can be accessible.
Yeah. The link is there already. Okay. Please, everyone, if you have any question, you may raise your hand or probably just speak up. You just unmute your microphone and then you just ask Dr. Hamwira if you have any other question.
Can I add something?
Okay, Dr. Dini.
Maybe Dr. Hamwira missed something on the brain pattern. So you ask Dr. Hamwira about the pattern, the specific pattern for specific situation. So actually,
yes.
For example, our colleague also did the study on identifying autism kids. So for autism case, if we looking at the brain pattern in terms of the brain wave, the delta, theta, alpha, and gamma, for specific case in autism, they will showing in the U-shape pattern. Okay, and for the normal kids is N shape.
Oh, it makes like you, I think. Oh, okay. Okay, okay. It's interesting. How about cancer, doctor? Is it possible to detect cancer using EEG? Brain cancer? Is it possible or not?
Not sure because never try about that.
Because this is non-invasive. I think it would be better if we have a non-invasive mechanism
But
rather than
for cancer, I think it's I'm not sure. I'm not really sure. But most probably it's more to the image processing rather than signal processing.
signal processing. I see. Okay, okay. Actually, okay, there's another question from Mr. Bayhaki. Have you ever tried to operate a robot or IoT devices using EEG signal?
Not yet.
Not yet.
Oh, not yet. Robot. Yeah, I mean, we don't have robot, but yes. As I said, we are now currently one of my students. I mean, FIP students with Dr. Dini as well. They are working on the brain-computer interface, not to operate robot, but rather to control the software, game playing.
I see.
The outcome is not here yet. We're still, developing it.
Okay. Is there any other questions you may other participant? Doctor, how about is there any different or any significant difference between closed eyes and open eyes for the signal or for the result?
Yes. So these, the eyes closed and eyes, I'm typing and talking at the same time.
Yes, sorry.
So eyes closed and eye open, it's standard. It's not only from us. We are following the protocol or paradigms also done by the doctors.
Okay.
So when they want to capture the brain's EEG form, they want to put the subject into a neutral state. Close their eyes and open their eyes. Yes, we actually did some play. We didn't record it. When you close your eyes, your mind is not really wandering. You are, the delta is more. Delta is more. But when when you open your eyes, because your eyes also working, so yes, you can see the difference.
I see. So it's not there yet because of the, the protocol, right? So it is all about the protocol of the taking data for brain. It should be in the mode eyes closed.
Yes. So it should be neutral. But of course, they are different. There are differences.
Of course, yeah. And the time still we have. Okay, I think. Is there any other question or not? Or else I will ask one more question, Doctor, before we close the session. Okay, there's Mr. Bayhaki. He told that it will be interesting if we can try to this EEG to blind people.
Yeah, I think it's interesting. If you are interested, you can contact me personally, or you can contact Dr. Dini. Probably Dr. Dini can leave your email address down there.
I think we can finish this session because the time is almost up. Okay. Do you have any closing statement, Dr. Hamwira?
Okay. Closing statement. Thank you for listening. Yeah, I mean, go to the papers, the student presentation after this. If you have anything to share with us, feel free to contact me or Dr. Dini. We can see how we can work towards it. It's a very interesting but challenging research area, especially we want to do it in computing.
Okay.
Thank you so much. Thank you so much for the,
okay, wait a bit. We need to take a picture, Doctor.
Picture.
Okay. I will ask the committee to take picture. Please open your camera. Miss Aulia Safira, please take picture of us. Let me ask the committee or not. Let me do the.
I will take the picture.
Okay. Please open all your camera. It's too noisy. Okay. Please let me know if you have done taking us the picture. Okay. Okay. I'll count to 3. 1, 2, 3. Okay. This is for the first page. Second page. 1, 2, 3. Okay, and the last page. 1, 2, 3. Okay, then I think everyone is taken for the picture. Thank you everyone for your for attending this workshop. Thank you also for Dr. Hamwira, Dr. Dini here also. Thank you for your very interesting presentation. Okay.